In this lecture, I'm going to present the hyperbola, focusing mainly on how to sketch it. As you remember, the hyperbola is obtained at the intersection between a double cone and the plane that's parallel to the axis of symmetry of the cone. These two branches form the hyperbola. As you can see, the hyperbola consists of two disconnected parts. It has two foci like the ellipse. It has two vertices. The segment between the two vertices is its transverse axis, and the midway between the two vertices is its center. As you can see, the two foci, the two vertices, and the center all lie on the same straight line. In the ellipse, we were concerned about horizontal or vertical major axes. In the hyperbola, we are concerned about horizontal transverse axis or vertical transverse axis, as we'll see in the next slide. This is the case of the vertical transverse axis. It also had the two foci, the two vertices, and the center. The two vertices are equidistant from the center. The two foci are at equal distances from the center, and all of them lie on the same vertical line in this case. So we are always concerned about whether the hyperbola has a vertical transverse axis or whether it has a horizontal transverse axis. These are the two cases that will make the standard forms of the hyperbola. Now I start by presenting a standard form equation of a hyperbola with a horizontal transverse axis. Details in the background of this equation will be given later. For this hyperbola, it can be compared to the equation of the ellipse. The only difference that we can see that here the y square is positive, but here the y square is negative. So in the hyperbola, we are concerned about the positive term, not about the bigger or smaller a and b. We are only concerned about which term is positive and which term is the negative one. We can also see that if we put the y square is equal to 0 to get the intercept with the x-axis, the x square will be positive a squared, so x will be plus or minus a. So the coordinates of these 2 points will be a and 0 and negative a and 0. On the other hand, if we put the x is equal to 0 to get the intercept with the y-axis, we'll get the y square is equal to negative b squared, which is a negative number, so there is no intersection with the y-axis. To get the coordinates of the foci are equidistant from the center at the distances c. So the coordinates of the foci will be c and 0 and negative c and 0. The relation between the c, a, and b, it will be given by c squared is equal to a squared plus b squared. If you remember, in the ellipse it was c squared is equal to a squared minus b squared, which was the bigger number minus the smaller number. In the hyperbola, it's simply their sum. So to summarize, if the hyperbola, the x squared term is positive, it will cut the x-axis. The foci, the vertices, and the center will all lie on the horizontal line, and the relationship between the c, a, and b will be given by c squared is equal to a squared plus b squared. The second standard form equation will be for a hyperbola that has a vertical transverse axis. The equation will be y squared over a squared minus x squared over b squared is equal to 1, where the y square is the positive term and the x square is the negative term. So this hyperbola will cut the y-axis. It will have no intersection with the x-axis. The two vertices, the two foci, and the center will all lie on the vertical line. The two vertices are at a distance of a units from the center, so their coordinates will be 0 and a, and 0 and negative a, being on a vertical line. They have their x-coordinate equal to 0. The two foci are c units from the center, so their coordinates will be 0 and c, and 0 and negative c. The relation between the c, a, and b is also c squared is equal to a squared plus b squared. So if we have the y square is positive, the two foci, the two vertices, and the center will all lie on the same vertical line, and the c squared will be equal to a squared plus b squared, and the curve will have no intersection with the x-axis. To know the background behind the standard form equations that we have presented, we have to know the hyperbola definition. A hyperbola is defined as the set of points in the plane whose difference in distances to two fixed points is constant. So if we take a point P on the hyperbola, d2 minus d1 is a constant. Taking another point, d2 minus d1 is a constant. And usually in deriving standard form equations, we take the coordinate axes, x and y, at the axis of symmetry of the shape. By applying this definition on the point B with coordinates x and y, the foci c and 0 and negative c and 0, we can use the distance formula to get these distances, pf1 and pf2. And we substitute in this equation, and through a series of algebraic steps, we reach the standard form equation that we have presented. The same can be done for the hyperbola with the vertical transverse axis. We'll also use the same definition and reach the standard form equation, which is y squared over a squared minus x squared over b squared is equal to 1, and c squared in both cases is equal to a squared plus b squared. What's really important to notice here that if the x squared is positive, then the transverse axis is horizontal. The center, the vertices, and the foci all lie on the horizontal axis, and they are equidistant. The two foci are equidistant from the center. The two vertices are equidistant from the center, and the relation between a, b, and c will be given by c squared equal to the sum of a squared plus b squared. Similarly, for a hyperbola with a vertical transverse axis, the two foci, the two vertices, and the center lie on this vertical line, and c squared is equal to a squared plus b squared, and the y squared is the positive term in this equation. In this example, we are going to sketch this hyperbola. First of all, we noted that this is a standard form equation, so the center is at the origin. Second, x squared is positive, so this hyperbola has a horizontal transverse axis, and the hyperbola cuts the horizontal axis in 2 points, which are its vertices. The number below the x squared defines the a squared, so a squared is equal to 25, giving a is equal to 5. The vertices are a units from the center, and on this horizontal line, so their coordinates will be a and 0 and negative a and 0, which are 5 and 0 and negative 5 and 0. To locate the foci of this hyperbola, we need to calculate c. B squared is the number in the denominator of y squared. C squared is equal to a squared plus b squared, so c squared will be 41, giving c equal to the square root of 41. The foci are c units from the center and on the horizontal axis, so their coordinates will be c and 0, negative c and 0. Accordingly, they will be negative square root of 41 and 0 and square root of 41 and 0. Another example, here it's required to sketch this hyperbola showing its vertices and foci. We can observe that this equation is in a standard form, so the center is the origin. In this case, the y squared term is the positive term, so the transverse axis is vertical, and the hyperbola cuts the y-axis. There is no intersection with the x-axis at all. The number in the denominator of the y square is the a square, so a is 5. The number below the x square is the b square, so b square is equal to 16, and b is equal to 4. The vertices are a units from the center, and being on a vertical line, their coordinates will be 0 and a, and 0 and negative a. So they are 0 and negative 5, and 0 and 5. To calculate c, c squared is equal to a squared plus b squared, simply their sum, so it will be 41, giving c equal to the square root of 41. Also, the foci are on this vertical line, and c units from the center, so their coordinates will be 0 and c, and 0 and negative c. Always remember to sketch the information that you have. This will make finding these coordinates very easy. What we are going to do here is that we are going to find the equation of the hyperbola with the given foci and vertices. First of all, remember always to plot the information that you have. So you plot the two vertices and the two foci, and make the following observations. The distance from the center to the vertex is equal to the distance from the center to this vertex, so the center must be the origin, and the line joining the two vertices is the transverse axis. So we can notice that the transverse axis is a vertical line. The hyperbola cuts its vertical axis in 2 points, which are the vertices, and it doesn't cut the x-axis. Having this shape, then the hyperbola equation can be assumed as y squared over a squared minus x squared over b squared is equal to 1. The y squared is the positive term, the x squared is the negative term. Now we have to find the a and b. The a is the distance from the center to the vertex. So it's clear that the a is 3. The b is not given. The distance from the center to the focus is c. So c is 5. And using the relation between a, b, and c, we can calculate b. B squared will be equal to 16. So this equation will be y squared over 9 minus x squared over 16 is equal to 1. Up to this point, we can now sketch any of these two hyperbolas. Whether it has a horizontal transverse axis or a vertical transverse axis, we can easily locate the center, the two vertices, and the two foci in any of these two cases. One more important thing that will help us sketch the hyperbola is the asymptotes of the hyperbola. These asymptotes tell us the behavior of the curve as x gets bigger and bigger, or as x gets smaller and smaller. So as x approaches infinity, this curve will approach these two straight lines, and as x tends to negative infinity, this curve will approach these two straight lines. These two red straight lines are called the asymptotes of the hyperbola. They also define how narrow or how broad this blue curve is. In this case as well, as x approaches infinity, the blue curve will approach these two straight lines, and as x approaches negative infinity, the curve will approach these two red lines. Now we'd like to know the equations of these asymptotes. We'll do it at first for this curve, which is a hyperbola with a horizontal transverse axis. As you know, these two asymptotes describe the behavior of this curve as x approaches to plus infinity or minus infinity. So to get their equations, we have to take the limit of this problem as x approaches to plus or minus infinity. The problem here is that the x appears in the numerator, so taking the limit as x approaches to plus or minus infinity will not be very useful. So we have to rearrange these terms. We start by taking the y squared over b squared in one side and all the other terms in the other. Then we multiply by b squared and take the x squared over a squared as a common factor from these two terms. Then we'll take the square root for both sides. This will give us x squared in the denominator. Now we can take the limit as x approaches to plus or minus infinity, and you can see that this term will completely vanish, and then the dominant term will be y is equal to plus or minus bx over a. These are the equations of the asymptotes. They pass through the origin, and they don't have a constant here. Also, one of them has a positive slope, and the other one has a negative slope. What really matters here is how to sketch these asymptotes. A simple way to do this is that we draw this rectangular box. An easy and simple way to draw it is that we have to go from the center on the transverse axis, go a units to the right and a units to the left, and then perpendicular to the transverse axis, from the center you go b units upwards and b units downwards. You'll get these 4 points, and then draw this rectangular box joining these 4 points and centered at the center of the hyperbola, which is the origin in this case. It's clear that the slope of this line, which is the diagonal of the rectangular box, is b over a, as if we calculate tan of this angle, it will be b over a. So the diagonals of this rectangular box completely define the asymptotes of the hyperbola. Now we'd like to find the asymptotes for this hyperbola. This is a hyperbola that has a vertical transverse axis, since the y squared term is the positive term. We'll follow the same steps. From the center on the transverse axis, which is vertical in this case, we'll go a units upwards and a units downwards. And perpendicular to the transverse axis, we'll go b units to the right and b units to the left. Then we'll have these 4 points. We'll draw a box that passes through these 4 points and that is centered at the origin in this case. And we'll join the diagonals of this box. These diagonals define the asymptotes of this hyperbola. To find the equations of these two asymptotes, we can see that tan of this angle will be A over B, which is height over the base. So the equation of this line will be y is equal to A over bx. It doesn't have a constant since it's passing through the origin, which is the center of the hyperbola. The other one will have the same equation, but with a negative sign as it has a negative slope. So to graph hyperbola that are centered at the origin, we'll follow these 4 steps. First, we locate the 2 vertices, knowing the A of the equation. Then we draw the rectangular box that we have just described. We join the diagonals of these boxes to obtain the asymptotes. And finally, we draw the 2 branches of the hyperbola, starting at the vertex and approaching these 2 asymptotes. Now we would like to apply these graphing steps on this hyperbola. This hyperbola is in a standard form, where the x squared term is positive, so it has a horizontal transverse axis. It can be compared to this equation, where usually you put the a square under the positive term and put the b square in the denominator of the negative term. So the a square would be equal to 36, giving a is equal to 6, and the b square is 9, so the b will be equal to 3. Having a horizontal transverse axis, the 2 vertices will lie on the horizontal line. Their coordinates will be minus a and 0 and a and 0. So they will be 6 and 0 and negative 6 and 0. This is the first step in our graphing process. Next, we draw the rectangular box. From the center of the hyperbola, we move on the transverse axis, which is horizontal in this case, so we move a units to the right and a units to the left. And perpendicular to the transverse axis, we move b units upwards and b units downwards. We'll get 4 points and then draw a rectangular box passing through these 4 points and centered at the origin, which is the center of the hyperbola in this case. In the third step, we draw the diagonals of this rectangle, and we have to calculate their equations as well. You can see that these diagonals pass through the origin. Their slope can be given by tan of this angle, which is b over a. So the slope of the asymptotes will be calculated as b over a, which is 3 over 6, which is equal to half. We have 2 asymptotes. One of them has a positive slope and the other one has a negative slope. In the last step, we draw the 2 branches of the hyperbola. They start from the vertex and approach the 2 asymptotes as x approaches infinity, or start from the other vertex and approach the 2 asymptotes as x approaches to negative infinity. We have also to calculate the coordinates of the foci. This hyperbola has a horizontal transverse axis, so the center, the 2 vertices, and the 2 foci all lie on the same horizontal line. Their y-coordinate is 0, so the 2 foci coordinates will be c and 0 and negative c and 0. We have to calculate the c at first. A squared is equal to 36, b squared is equal to 9. The c squared is given at the sum of these 2 squares, which is equal to 45, so c is equal to 45. This defines the distance from the center to the focus. So the coordinate of the foci will be square root of 45 and 0 and negative square root of 45 and 0. We can also graph hyperbolas which are not centered at the origin. So this is the standard equation that's centered at the origin. If you compare it to this equation, we can see that the center will move to h and k, and we'll get this shifted hyperbola. The relations between a, b, and c will be preserved. So for this hyperbola also it will be c squared is equal to a squared plus b squared. Also the distances are preserved. So the distance here from the center to the vertex is a. In the shifted hyperbola also the distance from the center to the vertex will be a. The distance from the center to the focus in the original hyperbola is c. In the shifted hyperbola also the distance from the center to the focus will be c. The only difference is that the coordinates here will be taken with respect to the center, which is h and k. Here all the coordinates are taken with respect to the center, which was the origin. The same can be noticed for a hyperbola that has a vertical transverse axis and that is not centered at the origin. So if we take this standard equation and move the center to H and K, we'll get the new equation, which is the shifted equation. This also has a vertical transverse axis, the shifted equation. It preserves the distances, so the distance from the center to the vertex will be also A. The distance from the center to the focus will be also C, and the relation between C, A, and B will be the same as the unshifted one. The only difference again is that the coordinates of the vertex and the foci will be shifted by H and K. Finally, we'll graph this shifted hyperbola. It can be seen that it has x squared and x terms, y squared and y terms. Obviously, the shift is not apparent from this form, so we will complete square with respect to the x and with respect to the y. We start by grouping the x terms together and the y terms together. Then to complete the square, the coefficient of x squared should be equal to 1 and the coefficient of y squared should be equal to 1. So we factor out the 4 at first and we factor out the 9 from these two terms. Then to complete the square, we add half the coefficient of x squared and subtract it. This will give x minus 3 all squared minus 9, and here it will be y plus 5 all squared minus 5 squared, which is equal to 25. Finally, we'll distribute the 4 over this bracket and the 9 over this bracket. So it will be 4 multiplied by x minus 3 all squared minus 36 minus 9 multiplied by y plus 5 all squared minus 9 multiplied by negative 25 is plus 225. We'll take all the numbers to the right hand side, which will add up to negative 36, and finally we'll divide by negative 36. We'll get this equation. In this equation we can make these observations. The y squared term is positive, the x squared term is negative, and the center is shifted to 3 and 5. So this is a hyperbola with a center 3 and 5, and it has a vertical transverse axis. This is the information that we have so far. We have a hyperbola that's centered at 3 and negative 5. The positive term is the y squared term, so it has a vertical transverse axis. The a squared is the number in the denominator of the positive term, so it will be 4. The b squared is 9, and we'll get b is equal to 3. And this is the center of the hyperbola. Now we'll move on to the first step of the graphing of a hyperbola, which is locate the vertices. Since the transverse axis is vertical, the center and the two vertices all lie on this vertical line. So from the center, if you move a units upwards and downwards, we'll get the two vertices. All of these 3 points have the same x coordinate. They will only differ in their y coordinate. So the y coordinate of this vertex will be minus 5 plus a, and the y coordinate of this point will be minus 5 minus a. Accordingly, the two vertices will be 3 and negative 3 and 3 and negative 7. The second step of graphing a hyperbola is to draw the rectangular box. We already have 2 points that this rectangular box will pass through. We need the other 2 points. The rectangular box will be centered at 3 and negative 5. To get the other 2 points, from the center, we move on a horizontal line that's perpendicular to the transverse axis, b units to the right and b units to the left. So we'll get these 4 endpoints, and we can easily draw the rectangle. If you want to calculate the coordinates of the endpoints of this blue line, we can see that these 3 points all lie on the same horizontal line. So all of them have the same y coordinate. They will only differ in their x coordinate. Since the center's coordinate is 3 and negative 5, the coordinate of this point will be 3 plus b and negative 5, and the coordinate of this one will be 3 minus b and negative 5, giving 6 and negative 5 and 0 and negative 5. That's why this point lies on the y-axis. In the third step, we draw the diagonals of this rectangle. These are the asymptotes of the hyperbola, and it's also required to get their equations. So we can get the equation of this straight line by getting the tan of this angle. It will be a over b, given that a is 2 and b is 3, so the slope will be 2 over 3. This has a positive slope and the other line has a negative slope. That's why it's plus or minus. To get the equation of these two straight lines, for example, this straight line, passes through the point 3 and -5, and it has a positive slope of 2 and 3, so we can use the point slope formula, which is y minus 5 over x minus 3 is equal to the slope. This will give these two straight lines, one time for the plus and the other for the minus, and we can simplify to get the equation of the two asymptotes. Finally, we'll draw the two branches of the hyperbola. We start from the center and approach the two asymptotes. And then we'll find the coordinates of these two foci. The two foci, the two vertices, and the center all lie on this same vertical line. All of them has an x-coordinate of 3. They will only differ in their y-coordinate. Also, the foci are at a distance of c units from the center. So, the y-coordinates of the foci will be 3, minus 5, plus c, and 3, minus 5, minus c. We have first to calculate the c. C squared will be equal to a squared plus b squared. So c squared will be equal to 13, giving c equal to root 13. So the two coordinates of the two foci will be 3 and -5 minus root 13 and 3 and -5 plus root 13. Finally, sketching this hyperbola is left for you as an exercise.